So we are live, sir. We will start this, sir. A very good morning to all. It's our great pleasure to have you all for the Knowledge 4.0 webinar series, which is one of the unique initiatives of Chennai Institute of Technology under the guidance of our chairman, Mr. P. Sriram, a successful first generation entrepreneur, a well-known industrialist, managing director of MK Group of Companies. Under Knowledge 4.0 series, we have been conducting webinar series such as technical webinar series, research webinar series, career guidance webinar series, and innovation webinar series. Today we have one-day online technical workshop on Industry 4.0. We have eminent personalities. We have Dr. Arunachalam from Indian Institute of Technology, Madras. He is going to talk about digital twin. And we have Dr. Swarna Ravindra Babu. He is the founder and CEO of Smart Systems Private Limited and professor of CIT. He is going to discuss about the industrial IoT part. And the afternoon session we have Mr. Rajesh. He is the AGM of Yaskawa Robotics, and he is going to discuss about robotics and automation solutions for the future of Industry 4.0. Chennai Institute of Technology was established in 2010 by our chairman, Mr. P. Sriram. Now our institute is being within top 10 institutes among private engineering colleges in Tamil Nadu. So it's our great pleasure and honor to have you here, Dr. Arunachalam sir. And Industry 4.0, it's a buzzword of the current situation, and every industry from OEM to Tier 1 and Tier 2, everybody is implementing the Industry 4.0 for the next level of advancement in the tracking in every level, from the production line and supply chain management. So tracking and all the activities have been coming under the Industry 4.0. So hopefully we may have a very good session and very informative and interactive session today. Thanks all the participants and thanks sir for being here. Now I request Ms. Varsha to introduce about our guest.
Good morning everyone. This is Varsha, pursuing second year mechanical engineering at Chennai Institute of Technology. It's my great pleasure and honor for me to welcome you all for the one-day online workshop on Industry 4.0 organized by Chennai Institute of Technology. Excellence is not being the best, it is doing your best. One such person is Dr. Arunachalam, received his Bachelor's of Engineering from College of Engineering Gindi, Anna University, and did his Master's degree from NIT, Anna University. And he further did his PhD from Indian Institute of Technology, Madras, during 2010. He's worked as a research engineer at General Electric GRC Bangalore, India for 3 years. Prior to joining IIT Madras, his research engineering includes centered around high performance manufacturing, which includes Industry 4.0 implementation and practice sensors, signal processing, advanced micro and nano level polishing process. He was awarded with the Best Student Project Showcase Award for the project titled IoT Enabled Smart CNC Milling Machine in Manufacturing Today Summit, organized by Aditya Birla Group and ITP Publishing 2016. He has published more than 90 plus research articles in journals of high repute. We are glad to have you, sir.
Thank you. Thanks for the introduction and thanks for arranging this. I would like to thank Dr. Maladi and Dr. Thinagaran and the team who involved in this arranging this webinar on Industry 4.0. And with this introduction, I will straight away go to the slides. And once you could be able to see the slides, please let me know so that I can move on.
That's a perfect, sir. Yes, sir. Slides are visible, and okay. we will go in the video off mode so that it will be easy for you to explain.
Okay. Okay. Thank you.
Over to you, sir.
Thank you, and good morning to all the participants. Kaalai Vanakkangal. So today's talk is on digital twins, a key enabler for realization of smart manufacturing. And a little bit about me, and I have Varsha introduced me about I have done PhD from IIT Madras, then moved worked with two different industries, then I moved back to IIT Madras as a faculty. And now my current role is as Associate Professor in Department of Mechanical Engineering at IIT Madras. And so the title, having a word on smart manufacturing, and before we go into digital twins, we will introduce what is smart manufacturing and why smart manufacturing is needed in this current industrial scenario, and what are all the key enablers for smart manufacturing, and how the digital twins is enabling the realization of smart manufacturing. We will see with some case studies. So manufacturing is a fundamental pillar of modern society and significantly contributing for employment and welfare. And this manufacturing industries consumes 1/3 of the primary energy produced, and that is the motivation also to introduce smart manufacturing. And you wanted to reduce the energy efficiency, you wanted to improve the productivity, and also you wanted to do manufacturing by reducing the environmental impact, and you wanted to develop processes, technologies, and methods which actually aiming at reducing the energy usage and material usage at the manufacturing activities without harming the environmental resources. So how you are going to enable this manufacturing to a smart manufacturing to carry out these activities in a seamless way. That is what we are going to see. And manufacturing has changed and it continued to change, right? From the beginning of the manufacturing shop floor, and all the machines were mechanical machines, and then we introduced automation through CNC, and now we are more driving towards personalization. That means everybody wanted a model of their choice. That means your manufacturing shop floor has the capability to accept different models and manufacture within the stipulated time, and that is a very challenging thing. So to adapt that personalization need, the manufacturing shop floor need to adapt and change themselves, not only by software means, also by hardware means. So how this can be done in a smart manufacturing way, that is what we are going to discuss. And today if you are looking at car manufacturers, we are more into kind of a flexible manufacturing system. That means we wanted to produce a particular model of car in a mass production, and with a sequenced production lines, and workstations are fixed, and it has a fixed hardware layout of machines in order to sequence the particular model of a car. And you wanted to change to another model, then you need to change your sequence of operations, and you cannot alter your hardware setup of your manufacturing shop floor. But what you need tomorrow is we need a decoupled, fully flexible, and highly integrated manufacturing systems. That means your hardware layout can be changed at any time depending upon the product varieties you wanted to manufacture, and not only by software means, you wanted to change the hardware layout as well. That is the term as reconfigurable manufacturing systems. And so you wanted to add intelligence to your system in order to accept different varieties of products. So this will be enabling to meet the customer demand of personalization. Every customer wanted. So customer will be a co-creator in designing a product. That means customers will be having a choice. Customer will be dictating the terms. Now, as a manufacturer, whether I have that facility to create the demand of the customers, rising demand of the customer. That is the thing which we wanted to enable tomorrow. And based on this, the new industrial model is aiming at improving the non-labor resource efficiency. First one, That means I wanted to automate and I wanted to reduce the valueless activities within the manufacturing shop floor. I wanted to automate certain low-skilled jobs in order to make use of that labors for other works. And I wanted to invest in sustainable inputs. In the sense, I wanted to invest more money on energy production. I wanted to reduce energy wastage within the industry. And that is enabling to create a new skilled jobs within the manufacturing organization. And I wanted to commercialize this competitive advantages. That means I have improved my non-labor resource efficiency. I have invested sustainable inputs. Now I wanted to make use of these 1 and 2 in order to take up the commercial competitive advantages, which are all capturing new customers. And I wanted to conform to the quality requirements of the customers. And I have time to think about what futuristic products I can manufacture, and I can think of it to create new business model, new business lines for my industry. So this is what the new industrial model. And what is a bold aim here is I wanted to have a zero environmental impact from its operations by 2020. Now we are in 2020. That means whatever businesses you wanted to do, and you wanted to have zero environmental impact, right? That is the bold aim of the new industrial model. And how the smart manufacturing is going to enable or enabling this new industrial model to be practiced across different manufacturing industries for realization of improving the productivity and efficiency of manufacturing systems by reducing the wastage. And so I wanted to improve the productivity, and it's very nicely said by Nobel Prize winner Paul Krugman. And productivity is not everything, but in the long run, it is almost everything. A country's ability to improve its standard of living over time depends on almost entirely on its ability to raise its output per worker. So the current manufacturing industries, I wanted to improve the productivity. And what way I am going to improve the productivity? What does mean by productivity? We will see some of the key enabling factors which actually improve the productivity. One is delivering value to the customer. That means do the right things before doing things right. That is very important. And depending upon the demand, depending upon the requirement, you just prioritize the work, log, and act accordingly, and manufacture the products as per the customer specifications. That is conformance, and you wanted to produce quality. And by doing that, you are going to deliver value to the customer. You are going to deliver value to the customer. It is one way of improving the productivity. And in a manufacturing shop floor, you wanted all the processes to be under control. And one thing you need to remember, do not overload processes, equipment, or people, right? If you are overload your processes, equipment, and people, then your uncertainty is going to grow exponentially. When your utilization is 100%, when you are stressing yourself, you will not be taking decisions properly, right? That is what your uncertainty is going to grow exponentially when your utilization is 100%. So ensure that you are not overloading your processes, equipment, and people. I have a person and who is working and delivering on things more. I cannot use him more and more because he is doing the work, right? I need to distribute the work. I need to free him in order to make him to think and come out with new ideas. That is applicable to machines as well as processes. And that means you are respecting your resources. And also you need to start focusing on the bottleneck processes in your operations. That means a particular operation is critical to the quality, but there is lot of variability with this particular processes. I wanted to pay attention to the particular process in order to get the processes under control, right? This is one way of improving another way of improving the productivity. And also I wanted to synchronize the processes as a system. Don't independently think into different machines. I wanted to look at every machines in a manufacturing shop floor. I wanted to look at manufacturing shop floor as a system. So because if you think about, you have a combination of different machines, and the machine processes a raw material and send it to another machine, and another machine's processing capability depends on what is the incoming quality of the processed component, right? So the variation is the biggest, one of the biggest enemies of productivity, and it need to be reduced. And when you can reduce, you have to think your manufacturing shop floor as a system, not looking into each and every entity with your manufacturing shop floor separately. You need to look into as a system level processes. And also you wanted to think about standardization of practices when you learn from it, modularization of practices, right? Modularization, that means you wanted to simplify it, and you wanted to reduce, and you make use of different jigs and fixes for different components. So, and also talk time, it's kind of a rhythm. The literal meaning of talk is a rhythm. It's a German word, and it's a time-phased production and just-in-time logistic. These are all the way in which you can synchronize the processes as a system in order to improve your productivity. And shorten throughput times. It's very important. That means what will you do? We talk about high performance manufacturing. High performance manufacturing is all about I wanted to improve the material removal rate. For that, what I will do, I will be increasing the speed and feed and depth of cut in a manufacturing, say in a milling process. By doing that, do you think I am improving the productivity? Productivity is what? I am increasing all these process variables, and I am producing the product as per these specifications. If I am not meeting the specifications and I am improving the production rate, that does not actually implies productivity improvement, right? You need to produce product faster without compromising on the quality, not at the expense of any of the first three roles. That's very very important. And so you make the lead times shorter and throughput times shorter to reduce non-value adding activities in all the manufacturing activities in a manufacturing shop floor. So these are all the ways by which you can improve your productivity. Now, to improve your productivity, I wanted to introduce smart manufacturing thing. So the smart manufacturing thing is going to improve the productivity. How? One is delivering value to the customer. Second is get processes under control. Is smart manufacturing is going to do this? Yes. How? We will see that. Synchronizing processes as a system, and it is going to shorten the throughput times, and it is going to continuously improve. That means the manufacturing shop floor continue to learn and update the knowledge. Updated knowledge will be utilized to continuously improve your production processes. And so this is the need. This is the current requirement of every manufacturing industries, aiming at improving the productivity, energy efficiency without compromising on the quality of the component produced, without any impact to the environment, right? If you are going to manufacture a product, what does it impact? How much carbon footprint the manufacturing of this product is going to give it to the environment? I need to have an assessment before even I am planning for starting a manufacturing organization. That is the current trend, right? So now we look into the smart manufacturing, right? Smart manufacturing, one thing is we have now the information technologies, and information and communication technologies growing like anything. And every person having a mobile, and your communication platform is well laid. Now you wanted to make use of this information and communication technologies to how to effectively, efficiently operate your production machines, manage and control the machines in order to improve the productivity and energy efficiency of production system with the least environmental impact. This is what about smart manufacturing. So it uses a real-time information in manufacturing processes by the original equipment manufacturer, with suppliers, leading to a whole new level of visibility throughout the supply chain, from the concept to the end of life of a product. Even after the end of life of a product, how I am going to recycle it, what is its environmental impact, right? Every activities of a component manufacturing, a part manufacturing, a product manufacturing company need to be visualized before even you are starting a manufacturing industries in reality, right? That is what the smart manufacturing is going to enable. So once you could be able to visualize, now you have laid your production shop floor and all the machines are ready for producing components. I wanted to produce the first part correct. I don't want to do any trial runs, no pilot runs. I wanted to produce the first part correct. How are you going to do that? You need more physical models, you need data-driven models, which is going to improve the traceability, flexibility for capacity management, and increasing the speeding of the product to the market by enabling smart manufacturing with real-time data, which you are getting it from the production machines, right? So this is what the smart manufacturing definition, and in the Indian context, the person in the picture is the president of Mahindra and Mahindra, and he very nicely put the intelligent manufacturing or a smart manufacturing as a jugalbandi of our IT skills that exist and our evolving manufacturing skills that become intelligent manufacturers, right? So you have India, particularly India, we are actually having much more matured software technologies, and now the manufacturing technology is also evolving, and it is the right time to make a jugalbandi of our IT skills along with manufacturing in order to improve your productivity and efficiency of your manufacturing systems, right? Ultimately, by doing that, you are going to do your business more effectively without any environmental impact. And so these are all the key enabling factors for Industry 4.0. And please remember, Industry 4.0 is not only for manufacturing. It is for any physical product which you think of it. You can talk about smart home, you can talk about smart products which make use of this industry as IoT and digital twins and cyber-physical system concepts. Together we can call as a Industry 4.0. So we started with introducing mechanization through electrification. Then we have introduced flexible automation through CNC machines, and we can see we have used robots and mechanized movement of components in assembly line in automotive industries. Now, what is next? I have all manufacturing shop floors. Now I have CNC machines, and CNC machines has the flexibility to accommodate different components by doing a programming, interactive programming, and you can make your machine to work on different product designs and for manufacturing. But yes, is it good enough for me? Can I not make the machine self-aware, self-adaptive to the situation? Can I make the machines more intelligent? That means a grinding machine can talk to a milling machine can talk to a shaping machine, right? So the machine-to-machine communications, a machine can talk to a robot, right? And machine can talk to all other connecting equipments which are all integrated in a manufacturing shop floor for producing the components as per the specifications without compromising on the quality and without affecting the environment. I wanted to make use of every machine to its maximum productivity, maximum efficiency. That is the role of smart manufacturing and so-called Industry 4.0 realization. So this is what we were moving towards Industry 4.0. It is a very broader topic to discuss. And some of the important key definitions which you need to know about Industry 4.0 is IoT, right? IoT is connecting sensors with your physical system and collecting the data and presenting the data. It ends there. Internet of Things ends there. Collecting data, presenting data, that's all, right? And now digital twins going to make use of this data in order to understand your processes, in order to understand your machines, right? And how this machines is working in a manufacturing shop floor, and is how the each and every components of the critical components of your machine tool is functioning, and what is its status, when to do maintenance, can I forecast the failure. Based on that, if I could be able to work with the data collected using the sensor, data is converted into information, information is converted into knowledge. I wanted to make use of this knowledge to control, right? The control can be human or it can be automated. Digital twin control is, you can optimize the processes, you can forecast how the system is going to work, but it may not require that you need to control. Automated control is not part of digital twin. That is what the differentiation between digital twin and cyber physical system. When it comes cyber physical system, you will be having a control, automated control. Based on the information which you are gaining, you assess the information and take decisions, make use of these decisions to enable controller which in turn going to reduce the speed, feed, depth of cut to make the production continue to work on to produce the component as per the specifications. Whenever there is a process deviation, it can be corrected. Whenever a particular component is malfunctioning, and that component will be replaced, or I will be using that component without its maximum capacity, and that will make the component to be used for some more time, right? That is all possible with cyber physical system. These are all these words, keywords you need to remember. IoT, just get the data and present the data. Digital twin, get it, present the data as well as process the data and acquire knowledge. Use that knowledge to forecast about the system behavior, and you can optimize the processes, and you can make a strategy to enable the persons to work with the machines. And cyber physical system, it has an automated control based on the decisions which you make out of the data analysis, enabling the controller to work as per the mode of operations which is required for your system to behave as per the specifications. Now, you know, this is the cyber physical system architecture, the 5-tiered architectures of JLEs, and you have a smart, this is what your IoT IoT ends here, right? Your smart connection level, you are just plug and play, the sensor is connected to the physical system, and the data is actually now collected, and it is represented, and you may not be using that for prediction. Here IoT here actually overlapping here as well as, because data presentation also comes here, and now data is converted into information, and that is the second layer. And third layer, you have cyber level. That means you wanted to represent the components and machines as a models, and you wanted to use different machine learning techniques to understand the data as well as the physical system operations. Now you wanted to make use of this for decision making, cognitive level. Now you wanted to make use of this decision to control your machines. That means you wanted to make your machines to self-configure, self-adjust, self-aware, and self-optimize, right? This is very important. This is the cyber physical system, and without configuration level up to cognition level, it is digital twin. Up to data and information, it is IoT, right? So this is what the clear demarcation or differentiation between IoT and digital twins and cyber physical systems. Now, the key differences and convergences of IoT, DT, and CPS given here. And if you wanted to say, talk about Industry 4.0, and it is making use of IoT, digital twins and cyber physical system in combination in order to control your processes effectively to improve its productivity and efficiency. And that is the level of integration, IoT, and next level is digital twin, and the overall level of improvement is cyber physical systems. So, which cyber physical system is a system of systems. It's actually, look at it, it comprises interacting digital, analog, and physical and human components engineered for function through integrated physics and logic. That is what you get an information and you get a decision, your action through control, and the physical state is manipulated and you are conforming to the standard, and also it is interacting with the environmental data and getting the environmental data, maybe a demand, maybe your environmental by which you are operating your systems, and human interaction is here. So by all these things combined together, you have a cyber physical systems. Now, little bit we go into the topic about the digital twins, right? It is from Colin Paris of GE. The digital, he represented as a digital twin as a living model that drives the business outcome, drives a business outcome. And how this is going to drive a business outcome, right? That means because it is about going to give you the working of any physical systems and operational performance of any physical system, what is the current productivity and how I am going to improve the productivity, what is the way in which I have to operate for improve the productivity. All these things can be enabled by digital twins. That means it is going to see, that means collecting data, it is going to think over analyzing the data, and through do, it is going to control the processes, or it is enabling the operators to control the process in order to improve its productivity and efficiency of your production machines. So it makes use of operational data and environmental data. Through that, it is going to continue to learn and update, and it is going to warn and predicting the failures. It is going to optimize the operations, and it is going to mitigation of failure events. It is going to forecast, it is going to control. So it is going to see, think, and do is actually the concepts of digital twins. It's very, very important to understand these terms and scenarios with this kind of explanation, right? And don't think digital twin can be only for systems. Look at this aero engine, and you have a compressor blades, right? And the fan blades, it suck the air and it's sent to the compressor, and compressor is going to compress the air, and compressed air going to your aero engine, that is a combustion chamber, and the hot gas which is going to actually drive your turbine which in turn going to run your fan. And when the hot gas actually comes out of it, a required thrust the engine is going to provide to your aircraft in order to propel, right? This is a engines as a system. I can create a digital twin for a whole aero engine. I can create a digital twin for each and every component as well. Turbine blade, I can create a digital twin, right? About some of the sensors, some of the data, what is the inlet temperature, what is the inlet pressure, that is good enough for me to understand the stresses experienced by the turbine blades under different operational regime. And also depending upon the different, this is the bearing. Bearing as a component, right? Even bearing has many parts in it, and bearing as a single component or a single product, right? But it is all assembled together to get a system called engine. So you can create a digital twin for turbine blade, you can create a digital twin for a fan blade, you can create a digital twin for a combustion section components, and independently, and combining everything together, you can have a digital twin for a system, right? That is what you need to understand. Digital twin is not only for systems, it can be for any component as well. Any parts of the component also you can create a digital twin. Even the operational performance you can create a digital twin. Please remember, it is digital twin is a software. It is a software platform imitating the behavior of your physical system with real-time data, but it has a brain. It has a brain. That is what differentiating. See, the one thing you need to remember, the language of communication for engineers is drawings, right? And now say the 3D CAD models is the language of communication. Now future will be the digital twin is a language of communicating between the engineers. The digital twin is going to be the language of communication. That means in a manufacturing environment, a designer, a manufacturer, a shop floor person, and a service a person, a customer, and the person who is using the product, servicing the product, and a person working on recycling the product, everybody will be having a common language accessing point is digital twin. Right? So now you think about the digital twin of aircraft systems, right? Aircraft it has so many components in it. Every component can have, but you wanted to understand your aircraft system behavior by collecting data and as well as physical models, how to operate this aircraft in order to get maximum profit, in order to maximum utilize every component of your aircraft, and that is the big thing which you can really realize by incorporating multiple digital twins and aircraft as a digital twin representation. Right? Even I can create a digital twin for humans. Right? That's what now you need. And I wanted to create a digital twin of humans, and I wanted to understand the heart. Right now, I have done some testing. I have understand my functioning of my heart and what is the level of degradation my heart and its components. And now I wanted to understand what is the how much time I spend my time for exercising, how much calorific value of food I am eating, and based on that, can I actually understand forecast the behavior of my heart? If I could be able to forecast the behavior of my heart, and I can decide about how much time I am going to live peacefully, right? You can understand. That is what it's a diagram representing, it's a picture representing kidney. How kidney malfunctioning is going to affect heart. How heart malfunctioning is going to affect your kidneys interacting. This is one system. This is another system. Right? Heart is one system within your human body, and kidney is another system within the human body. Each one has its own functions, but ultimately both are interacting by some means. What is that interaction mode? And if my heart is getting degraded, what is its effect on my kidney? If my kidney is going to degrade, what is its effect on my heart? If I could be able to picturize that, I can really understand what kind of food I need to take intake, what is the calorific value of food I need to intake, what is the kind of vitamins I need to sustain myself for to live longer. Right? So the digital twin concepts is going to enable you to improve your productivity and efficiency. That is what you can think of. This is all futuristic, and currently also a lot of development going on in this area. All right, and this is another very easy representation of a digital twin. Our transport bus, and my native place is Kanyakumari. I used to travel by, in the 90s when I used to study in College of Engineering, Ginty. I used to travel by a bus called Nesamani Transport Corporation from Kanyakumari to Chennai, right? And now I wanted to understand what is the current condition of the bus when it is starting from Nagarkoil, and during the running hours, I by utilizing a lot of sensors, I wanted to collect a lot more informations, and these sensor data analytics will let me know what is the condition of critical component of my bus engine. Right? Engine is the heart of your bus transport. And I wanted to understand every critical component of my engine by collecting a lot of sensors. And the tire condition, I wanted to understand fuel and quality of your other components within your engine. You need to understand what is the exhaust pollution level by which the engine is actually producing it. I wanted to understand. By making use of these systems, I'm nearing Madurai. Say I'm nearing Madurai, and I could able to understand my tire is going to release it, sir, and there won't be any air, and I cannot maneuver my bus. And now I can decide about go to the Madurai bus depot for correcting correcting some of the aspects of my bus and continue to move forward. Right, I don't want the time by which the passenger reaching the Chennai to be delayed. What I will do, I will be asking for a spare bus from Madurai. Everything is now automated, seamlessly integrated. Right, this is what the digital twin can enable. Fuel usage, right, and I can inform about the how many passengers traveling, every information now available. If I click the digital twin of a bus, it will be giving me all such informations. How many accidents the bus undergone, right, what is the starting year, date, time, and what until now how many kilometers the engine run, right, and when what is the maintenance due date for. It is not for time based maintenance, not a scheduled maintenance. It is all predictive, preventive maintenance, right, because I have sensors. This will be informing me about the condition of bus. So I wanted to integrate, and I wanted to have physical data comes in. I wanted to collect data from the buses and its usage. Now all these data are available, and these data are available with service engineer, passenger, and the emergency helpline, drivers and conductors. All these stakeholders associated with your bus transport system now will be having all these informations together. So this is the best example by which you can explain your digital twin concept. Now, when it comes to manufacturing, right, the more it's a more powerful tool, and you are going to help. The digital twin is going to help in conceptualization, comparison, and collaboration, right? So, because concept, you can able to share the common theme of data, and if you are if you could able to having a shared understanding by drilling down into the digital twin data representing your processes and system, and you can create shared conceptualization, right? That means view of different people can be combined together in the digital twin product in order to improve your productivity and efficiency of your production machines in a shop floor. So conceptualization is going to help you, and it is going to compare, right? Comparison is very effective tool. You need to compare how much deviation. Yesterday, what is the process output, and today the process output is different. Why? Right? It will be allowing you to rethink your way in which you are actually producing the components. So comparison is very effective tool, and the comparison will be enabled by digital twin. Also, digital twin is going to enable collaboration, right? Because it is providing a product centric view. That means everyone in the organization populates and consumes the information in a form of a digital twin. That means the digital twin information as a replacement for physical resources. This is what will be a very effective usefulness of your manufacturing. When we talked about why you need smart manufacturing, all these things now getting highlighted here by doing conceptualization, comparison, and collaboration. Okay, so now it's all about data analysis to decision making, right? So don't only think about data. Don't only think about data. You collect sensor data, and you do a lot of processing of data, and you do diagnosis and prognosis. This is very important terms. Diagnosis deal with detection, isolation, identification. Detection, any abnormal event can be detected, detection. Isolation, I wanted to isolate where the abnormal event comes from which component the abnormal event comes from. I wanted to isolate. I wanted to identify how severe the fault is from a particular component. How severe, whether I need to take a shutdown, I need to shut down the operation, or I can continue the operation for some more time. So the diagnosis need to be understood by collecting the features from sensor data. And I wanted to do prognostics. Prognostics is predictive diagnostics. What it means, I wanted to forecast when the system is going to fail. I wanted to forecast when the system is going to fail. By utilizing the operational data, environmental data, I wanted to predict the life of every critical component associated with your machine tool. If I could be able to predict that how much remaining life is available, based on that I can make a decision in order to control your processes, to control your machine, and adaptively in order to improve its productivity and efficiency, right? These are all the different. And also, don't think about only data. You can also have system models, right? You can create mathematical models, you can create analytical models, you can create finite element models for your physical systems, and you can collect data. These data can be go as an input for your simulation models, and you simulate for different scenario and get some operational profile of your parameters, and use your data to tune your operational parameter in order to make use of this for decision making. So you can use data as well as physical models in order to do diagnostics and prognostics. This is a key enabling factor for smart manufacturing, right? Smart manufacturing in a detailed way is that you wanted to work with data, you wanted to work with physics of operation in order to understand your machines and its functionality to improve its productivity and efficiency. Again, without any impact to the environment, without any environmental impact, I wanted to produce products, right? So now this is all about, we have learned about the different concepts of digital twins. We have discussed what is smart manufacturing, and we explained the smart manufacturing in Indian scenario, and we have a long way to go, but we have a lot more inclination than other countries in enabling smart manufacturing in our manufacturing industries, and this is the right time. And why you towards Industrial 4.0, about that, and different elements of Industry 4.0 terminologies: IoT, digital twin, cyber physical system, and the CPS 5-tiered CPS architecture of JLEs, and difference and convergence of IoT, DT, and CBS, how this enables your Industry 4.0, cyber physical system in bit detail, and concepts of digital twins. We discussed it's seeing, thinking, and doing, right? So that's why it is a living model. It's a living model because it thinks over and also it acts upon to the processes. And digital twin not only for systems, it can be for processes, it can be for components, and it can be for systems, it can be for system of systems. And digital twins, but much more explanation with the human interaction, and transport bus, just enabling a practical scenario where we can use digital twin in manufacturing. And now finally, in an elaborative sense, what the digital twin consists of. It consists of all these blocks where which data and physics are utilized for diagnosis and prognostics of every system for its improving its operational performance. Now we will see some examples of digital twin realization, right? This is the work of my PhD scholar, and we have a digital twin as an information sharing platform for smart manufacturing. And what is this all about? The grinding wheel, right? Grinding wheel as a digital twin we have created, and we have given a pre-product knowledge for this digital twin. Digital twin is a software, please, again and again, it's a software platform. And now this grinding wheel, I wanted to, suppose somebody wanted to select a grinding wheel for a particular material, particular operational strategy, and what is the kind of how will you select a grinding wheel? That knowledge we have incorporated as a software along with the grinding wheel digital twin. That is called product pre-knowledge. It is coming from the manufacturers. What is the kind of abrasive? What is the kind of bond material, right? what is the kind of bond material, what is the abrasive material, and what is the bond volumetric percentage, what is the abrasive volumetric percentage, and physical properties of the grinding wheel is saved as a pre-product knowledge. Now all these pre-product knowledge are actually fused into written into a RFID tag, and which is stick to the grinding wheel, and this RFID tag will be read from the grinding wheel in order to understand about the grinding wheel and its properties and its usage, right? And also we have real-time information data that comes from the motor current sensors, and which is the current signals are obtained from in a real-time usage of the grinding wheel from the grinding machine spindle motor current. And by making use of this current, I will be understanding how the grinding wheel is going to degrade, when to activate the dressing of the grinding wheel in order to retain the sharpness of the grinding wheel to continue the process. That is the process and the end of life information through motor current signature. And also we have developed a physics-based model that is because the grain level wear is having three different mechanisms: attenuation wear, wheel loading, grain fracture, and bond fracture. And we have the physics-based model developed, and this will give me the volumetric information with time dependent with respect to time, based on the material properties, process parameter, and grinding environment. So now you have a data-driven model, physics model, and this information go through this Raspberry Pi, and it goes to the local database, and through Wi-Fi router it goes to the cloud server, and you can get this information to your mobile. Who are all will be having this information? The customers, operators, service engineer, and management of the company will be having this information together, right? Because now its mobile communication is very effective. You can understand how the product is operating. Customer 1, customer 2, customer 3, what is its performance? Is it performing well? Can I improve my product to improve its performance? What is the learning I am getting it from the product which is performing? Right, all these data are captured in real time, and I will be using to redesign my system in a better way, and also I will be using it to improve the productivity and the efficiency of the production process in a customer side as well. So I am using a digital twin of a grinding wheel, right? Digital twin as a grinding wheel as an enabling of smart manufacturing platform, as an enabler for a smart manufacturing. Now, this is a reference paper, and you can, in ASME Journal of Manufacturing Science, we have an article, and you can, for detail, you can study this. You will get a lot more information. And also a digital twin of a machine tool spindle, right? Machine tool spindle is a critical component, and because in a milling machine, say in a milling machine, it is going to hold the tool tip, and the tool is going to interact with your workpiece to remove the material and produce the component as per the specifications. Now, the machine tool spindle has a lot more components, and you wanted to make use of sensors to accelerometer and thermocouples and the speed sensor. Utilizing that, you wanted to extract features, and you wanted to predict the chatter, presence of chatter in your machine tool. That means particularly the tool tip vibration is going to produce surface degradation of the component produced. Now, utilizing that information, you wanted to send it to the controller. Controller in turn driving your power amplifier, and power amplifier is going to actuate your piezo actuator in order to dampen out the vibrations to reduce the chatter, right? This is how the digital twin of a machine tool spindle look like. It's work by Kawa et al. In 2017. They have published a paper in CARP Annals of Manufacturing Technology. And so this is, if you look at it, you have a torque sensor, temperature sensor, current sensor, displacement, flow rate, vibration. These are all sensing. Now you have a decision making, thermal error, unbalance, damages with the bearings and other components, tool wear, breakage, chatter, collision of your spindle, tool tip. All these things are you have calculated or estimated from the data which you are getting it, as well as the physical models. And now the decision is made, and decision is going to enable your controller controller is going to produce, compensate for thermal error, active balancing control, and it is going to enable as well condition-based maintenance, right? So the control will be done by the embedded actuator with the machine and the CNC system, and as well as the operator can work onto the machine in order to reduce the chatter, to bring back the production process effectively to produce the components, right? This is another example of digital twin. And process twins. We have used a sensor called acoustic emission to understand the process of the die singing electrode discharge machining process. And this is a dielectric tank. We have fixed a acoustic emission sensor onto the tank, and you know the process of electrode discharge machining. And in between tool and workpiece, the discharge happens. The discharge is going to create a shock waves, and shock waves is going to come and hit the tank. I am going to pick up that shock waves which is hitting the tank to process it, to understand the process. More the shock waves, the process is more effective, and that will be helping me to understand the chosen electrode is correct or not, what is the thermophysical properties of the workpiece. All these information I could be able to get it from this sensor data in order to improve the performance of the process, ultimately aiming at improving the productivity, right? And this is the acoustic emission signal, and I don't know how much time we have.
Please, you can go ahead, sir.
Okay, thank you. So, and this is a typical signal, and it is the onset of the burst, and then it is the end of the burst, which you could be able to see. And we wanted to analyze this AE signal. Look at it. When I use different electrode, this is for copper electrode and copper tungsten electrode and graphite electrode, the workpiece is steel. I wanted to understand which one to use and look at the amplitude and frequency plot of your acoustic emission signal, and look at the graphite electrode is having more energy here, and so we can use the copper electrode, we can use the graphite electrode as the best one for your producing this component, and the AE RMS value also shown here. And this will be helping you to identify the best tool material in terms of MRR for a specific work material and process condition. So I am going to make use of this AE signal for electrode selection. Also, AE, I can use it to identify what material actually I am doing a machining, right? What material I am doing a machining. When you are having a AE RMS value, look at it for the titanium and D2 steel under different processing conditions. And the AE RMS value for your D2 steel is high than your titanium. Titanium exhibits poor machinability in terms of electrode discharge machining. So by utilizing this information, I can understand what material the machine is processing. I can understand the material type, and also whether the flushing is effective or not. Flushing is to remove the debris collected between the electrode and the workpiece, and we have done the flushing at 1.2 by 4 bar and 1 bar and 0.5 bar, and you can see that at 1.25 bar your AE RMS is more, that indicates sparking activity is good. So I can select your pressure of your flushing pressure 1.25 as a best condition. This is just using an acoustic emission signal. I can understand and confirm the selection whether it is correct or not. So this improve the productivity. So this is a AE signal is utilized to understand the process mechanism more effectively, which in turn leads the productivity improvement. So I can say this as a digital twin, but the digital twin, it is a process digital twin. This is a reference you can refer. We have a publication in this area, investigation on the effect of EDM process variables. And now this is two examples. So we have shown a grinding wheel what we have discussed about is digital twin. What we have done in IIT Madras, we have created a digital twin of a grinding wheel, and how this enabled a smart manufacturing initiative. Also, we have a digital, and it's not our work, and it's a work of CAT all, a digital twin of a machine tool spindle, and we have a process digital twins. Like this, we have more number of articles and more number of work we have done in this area. For considering time, I'm representing only a selected articles for you to learn. So now, what is the challenges we have in realizing Industry 4.0, right? We need a lot more people coming together to work as a team in order to realize the Industry 4.0. It is not only academicians and the industry people has to come together along with academicians and researchers have to come together, because it has a lot more big data analytics you need, because you are going to deal with the data, volume of data, velocity of data, variety of data, velocity of data. You are going to deal with big data. You need autonomous robots. You need a lot of simulation studies, and you need to integrate organizational level changes you need for realizing Industry 4.0. Even many of our industries doesn't have a CNC machines. They still make use of manual machines. Can I not do Industry 4.0 for manual machines? Yes, you can do. Who said you cannot do? You can do, but the level of integrations will be top first two levels of integrations, right? You may not be having a very effective control, or you can retrofit and convert your manual machines into CNC machines and realize Industry 4.0, right? All these technologies are needed for realizing Industry 4.0. And what challenges, right? You have lack of unified leadership, coordination difficult within the company, right? Even one company we have visited, we wanted to implement IoT, and they, even the machinists who work on the machines, really suspecting what these people are going to do, whether he is going to monitor me, how much I am working with the machines, right? It is not that. We are actually going to monitor the machines, how it is performing, right? And also it is, that is not only, even how effectively people are utilized within the manufacturing shop floor, also a role of Industry 4.0. And data ownership, lack of courage to launch radical digitalization plan, in-house talent, integrating data from various sources with the initial connectivity, lack of knowledge about technologies, right? These are all the challenges for realization of Industry 4.0. And only we talk about Industry 4.0. Am I having an enabling classrooms for teaching Industry 4.0? Can I bring an industry to a classroom? You have all these web connectivity. Can I make my students to interact during the study stage itself with the industry persons, getting the problem, providing a solutions, and interacting with them, two-way communications with the machines, learning it, right? All these things are enabling factors, factory to classroom communication for an effective knowledge transfer, which will be enabling a Industry 4.0 sustainability. This is very, very important. We need to adapt this in every engineering. And very interesting, why we need to embrace digital twins in times of coronavirus. I don't want to go to office. I want to sit at home. Still, I wanted to manage my manufacturing shop floor without any humans. Is it possible? Yes, possible. It can. So that's why the digital twin can enable this. Right? I wanted to maintain a social distancing, and I don't want people to be getting communicated not communicated. People in person to work with the machines, I don't want to allow. I wanted to make use of these people to monitor the progress of production by sitting at home, by communicating with the machines through digital twin as a language. Is it possible? Yes, it's possible. Even I can create a digital twin of a coronavirus, where it's originated, how it is spreading, what is its spreading dynamics, right? The rate at which it spreads, with the data, with the physics of its spreading, what is the humidity, what is the temperature, what is the spatial distance, and the spatial variation, uncertainty in propagation, and what is the probability of this a particular virus is going to die, right? I can create a digital twin of this virus, and it is very, very important to the going forward. We will be embracing this digital twin technologies more and more to enable, right, the current lockdown aspects, to enable, right? We wanted to work, our industry wanted to work, and how are you going to work? How you are going to enable, right? Only if you embrace digital twin technologies, right? And in research in IIT Madras, this is what the research we do, mainly on high performance manufacturing and to improve productivity, quality, cost, and environment. And we work on tooling, we work on monitoring and diagnosis, and we work on machine tool drives and bearings, and we work on metrology as well, right? And this is a lab we have in IIT Madras in manufacturing department, mechanical department in manufacturing engineering. We have Industry 4.0 and Smart Manufacturing Lab. These are all the enabling technologies and products which we have developed and as a digital twins. And the future research directions are smart factory. I told you I wanted to operate the whole manufacturing activities by sitting at home. Right? It's possible we can realize this, but it's long way to go. Right? Don't think about IoT is Industry 4.0. Please, it's not that. Right? I wanted to provide intelligence. I wanted the machines and system to be adaptive by getting the data. It's not that easy. Don't talk about data. We are talking about, so far the discussion, we are talking about data. The data, you need a clean data. Clean data will enable you to develop this models very easily. But when you have data which is sparse, unclean, right, then discontinuous data, how are you going to deal with uncertainty of your data? These are all challenges. And yeah, I'm coming to the final slide, right? So I hope you are all picked up some of the important points here. We have discussed about the digital twins, some examples: spindle, grinding wheel, process twins, and what are all the challenges you are going to facing for realization of Industry 4.0, and the educational future perspective, how the human resource need to be developed or for sustainable growth of Industry 4.0, and in this lockdown period, and how going forward, how we have to embrace, hold on to digital twins for enabling the operation of all your manufacturing shop floors more effectively and efficiently. And research at IIT Madras, what we do as a group. And this is what the final message with this I wanted to complete, right? I am a vivid fan of Magagavi Bharadiyar, and I hope you are all understand Tamil here, right? Very nicely he put forward his thoughts in this poem. And in the Puvidanil Valam Marangalum, Inba Narmalar Punjadi Kuttamum, and the Marangalai Sunda Kodigalum, out of the Muligai Puntu Pul Yavayim, Yendu Tuli say the Valvanavo, Manudar Ulavidinum, Vitnadavidinum, Varambu Katavidinum, Anti, Neer Paichavidinum, Vanulag Neerdarmil, Mandir Marangal, Vagai Vagayaga, Nerkal, Purkal, Malindurukumanto, Yadanarku Manjilagain, Manudare, Nivirian, Madatai, Kaikondamin, Padubadal Venda, Unudalai Varutadir. Last two is very important. ஊனுடலை வருத்தாதீர் உணவு இயற்கை கொடுக்கும் உங்களுக்கு தொழிலிங்கே அன்பு செய்தல் கண்டீர். Very, very important message in this lockdown period. We respect nature. All these digital twins, cyber-physical systems, Industry 4.0, all are enabling factor for sustainability. I don't want to affect the environment. I wanted to do business without any impact to the environment. Can I do it? If you can do it, do it. Otherwise, no business for you here. Now, the lockdown would have made you to understand. Don't, right? Nature will yield food. Agriculture will yield food. What is your purpose? Your purpose is love each other and spread the message of love to everyone. Right? It's very nicely he put forward these thoughts. It's very important to protect your environment, all your digital twins, cyber-physical system, Industry 4.0, all are enabling technologies for sustaining your planet for coming years. Right, with this I will complete. Thank you so much for all listening. I will take up some questions.
Thank you so much. Thank you so much for wonderful presentation, sir. The way in which you have taught is highly amazing. So I think so even layman can understand the language what you have talked. So that shows your how you expertise in this particular scenario. So thank you so much, sir.
Thank you.
Thank you so much for your kind presentation. Let us have some few questions.
Thank you, sir. Yeah.
Sir, how long it will take for a particular traditional industry to convert to Industry 4.0, sir?
If I am ready to make the organizational change, I wanted to now see even machine tool manufacturers. So only I am talking in terms of production of engineering goods. Okay, and I have everything, infrastructure, everything in place, right? It's even you can start an industry as a Industry 4.0 enabled one. No, but I have already having an industry where I have manual machines, CNC machining combinations, and how I am going to enable every machines communicating with each other. Now I have to upgrade my manual machines, right? It is only I am talking about in a shop floor environment, but all my machinists and shop floor persons are ready to accept these changes. I need to first educate them. I need to educate them. I have to educate my organization, right? It is not. It's not a vertical integration. It's a hard way of integrating because it involves people, it involves machines, and the machines has to have the capability to accept the communication through IoT and digital twins. I wanted to have the infrastructure in place, but if I have a manual machines, what I can do as an Industry 4.0, yes, you can do. You have a manual machines, that manual machines operated using a 3-phase AC induction motor. I will be putting a power cell and I will be getting how much power the motor is using every day, and can I effectively reduce the usage of energy by the motor. By doing that, I am improving the productivity without compromising on the quality. I am doing energy efficiency auditing by introducing power monitoring of a motor. That is what I can do. It is Industry 4.0 again, right? IoT, you are doing an IoT, you are collecting a data, you are representing a data, and manually you are controlling your processes. Right, so it's all depends on what infrastructure you have by which you can implement this. Thank you. Next question. Is it fine? Am I answering your question?
Yes, sir. Fine, sir. Fine, sir. Thank you, sir. Thank you, sir. So our next question. Sir, so APS asked this question. So what are technologies which are powering the current and next generation digital twins?
What are all?
What are all the technologies which are powering the current and next generation digital twins?
See, very important. You need to understand. Now, mainly, I told about diagnostics and prognostics. Diagnostics is detection, isolation, identification. Prognostics is about predictive diagnostics, forecasting the failure, right? That means how accurately I can predict the failure of the component. That is what, if my accuracy is 100%, I am 100% ready with the digital twin for implementing a practice. But right now, you cannot think about 100% prediction accuracy for the models which are all available. Just to think about even a small bearing which supports your rotating machineries. The bearing is, I wanted to predict the life of the bearing. I can use a vibration sensor, I can use a motor current sensor, I can use a temperature sensor, right? How accurately I can predict the failure of a bearing. The bearing is going to fail by another 10 minutes. Can I predict it more accurately? In a laboratory environment, it is possible. In a complex operating environment, And when the mode of operations are different, the environment is different, predicting accurately the bearing failure itself a challenge. Then you think about a machine tool. Machine tool has more components, right? But now you have technology for communication is embracing your development of digital twins, right? You need augmented reality, you need virtual reality, you need highly accurate physics and data driven models for realization of accurate digital twins, which can be deployed and utilized by all the stakeholders in a manufacturing supply chain for improving its productivity and efficiency. Is that fine? Am I answering your question?
Fine, sir. Fine, sir.
Thank you.
Thank you, sir. Thank you so much.
Thank you.
So much for your participation, and it was very wonderful, sir. Personally, I was telling it took me to college days and listening lectures from professors on those days.
Thank you so much. Thank you so much. And this final photograph is what we wanted it.
Yes, sir. Yes, sir.
It
Yes, sir.
shows we wanted to protect the nature, and by enabling all these technologies, do engineering to preserve the nature. That's a slogan that will make us to live longer and generations to come to enjoy the nature, right? And yeah, with this, can I drop or still more?
This time, உங்க தமிழ் பட்டுக்கு ரொம்ப வாழ்த்துக்கள் சார். நல்லா இருந்தது. Thank you so much, sir.
Thank you.
Thank you, sir. Bye, sir. We will meet in some other occasion, sir. Thank you, sir.
Thank you so much.
Participants, thank you so much. So we will break for we'll break for half an hour, and the next session will be started by 11:15. Please join the live by at least 11:10. So the link for the session is going to be sent through the group as well as mail. Okay, so please available at 11:10 itself in the live room, and the session will be started at 11:15. Thank you so much.